So computation is essentially comprised of stored information and ways to manipulate that stored information. Classical computers use bits and gates, and quantum computers use qubits and something we call unitary operations, which I'll describe later. The reason we care about quantum computers is that they can solve certain types of problems inherently faster than others, than classical computers can solve them. And so I will go over classical computers a bit. They use to store their information, and so a bit has one of two values, 0 or 1, and it can't be anything in between. And we can use bits to represent numbers. So for instance, this string can represent 1, and this string can represent 2. And then once we have bits, we can do operations on them. For instance, we can use something called a NOT gate to flip a bit from 0 to 1, or 1 to 0. And here I have a NOT gate operating on 3 bits at the same time. You can also have more interesting gates that take in 2 qubits, 2 classical bits at a time, and have an output, such as addition. Now, qubits are similar to bits in that they have 2 energy levels, which we denote 0 and 1. And the difference between a qubit to an ordinary bit is that it can exist in a superposition between 0 and 1. And this is the notation for that. And what this notation means is that when it is in the superposition, so by the way, A and B are numbers, and they correspond to the probabilities to find the qubit in the state 0 or 1 respectively. So A is, it's actually A squared is the probability to find the qubit in state 0. And so block sphere is a way we can visualize the state of a qubit, where we can have this arrow pointing straight up if it's in the state 0, straight down if it's in the state 1. And if it's in the superposition, we can have it point, it'll point somewhere in the middle. So for instance, if the arrow were pointing in the direction of the x-axis, it would be in this superposition where A and B are both 1 over the square root of 2. Which would mean that we have 50% chance of finding it in the state 0 and 50% chance of finding it in the state 1 when we choose to look. Okay, now quantum gates are the ways we operate on bits. And these are unitary operations. And what a unitary operation does is it, given an initial state of the qubit, you apply this unitary and you get this altered state after some time, which is the desired behavior of a gate, because you give a gate a set of initial bits, qubits, and then it will operate on them, and then you have this desired state when it is done. And so here's an example of a quantum NOT gate. If you give it a qubit in the initial state 0, and you put it through this gate, then it will end up in the state 1. A NOT gate can be given a superposition state. So if you're given this superposition state, it will simultaneously flip the 0 state and 1 state, so it ends up in this superposition. Fortunately, my graphics aren't three-dimensional, but in this case, the x-axis is pointing directly at you. And so essentially, a NOT gate is flipping the arrow 180 degrees around the x-axis. Another example of a gate is a Hadamard gate. If you give the Hadamard gate a state in the state 0, it will actually prepare superposition for you. and the end is a superposition between 0 and 1. And in this case, the x-axis is actually pointing to your right or left, or this way. And it's actually, it's A and B are, again, one of those vertices. Okay, so ideally a qubit in its physical system will exist in an environment very sheltered from outside noise. This is never really the case. It always interacts with its environment. In my project, I modeled the environment as a cavity, which is a harmonic oscillator, for those of you who know what that is. And this qubit cavity coupling, or the coupling being this interaction between them, will create undesired evolution, and so it will change the qubit state over time in a way we don't want. And this is one physical system of a qubit in a cavity. Here we have this qubit, and its immediate environment is this cavity, which is some strips of metal that make up a transmission line. So there's this method called dynamical decoupling, which is used to minimize this coupling with the cavity. And it is achieved by driving the cavity with pulses of light. In the case of the system I showed you here, it's microwave light, microwave radiation. And this, if the pulses of light are just right, they will eliminate the interaction between the qubit and the cavity. And if the light pulse is on resonance with the qubit, meaning that the light pulse's frequency is the same as the frequency corresponding to the difference in the qubit's energy levels, then this light pulse can also have a big effect on the qubit, even though we are using it to drive the cavity. So since we can use this light pulse to control the qubit, it is an ideal candidate for a gate. And here is a simple light pulse where this black envelope is what we call the envelope, and the red is gives you the frequency of the light. And another thing is that if the light pulse is off resonance with the qubit, it will have very little effect on the qubit. So if we put two qubits with different frequencies in the same cavity, we can drive one with the light pulse of its frequency without having too much of an effect on the other, which is good. And if we can get two qubits in a gate, then it's easy to act two qubit gates on them as well, which are essential for quantum computing. And so my project is concerned with finding these pulses, finding the pulses that result in gates, in the desired evolution caused by gates, when the qubit is coupled to the cavity. And to do this, I'm using a numerical technique called gradient descent pulse engineering. And the way this technique is an algorithm that maximizes a fidelity function. The fidelity function is the similarity between the desired evolution, the evolution of gate cause, and how similar that is with the initial control pulses, or the control pulses that this algorithm guesses. So essentially, it's given a set of control pulses which are guesses, and it uses these control pulses and the dynamics of the system to find how these control pulses will change the evolution. And the guess will have some error, and it will use this guess to compute a new guess with less error. And so it will do this over and over until it converges on a very good answer. Okay, so one example of a gate is a memory operation or an identity operation. And this operator does nothing on the qubit. It just maintains its state. And in the presence of a qubit cavity coupling, the identity operator is returning the qubit to its initial state after its state has been evolved by the qubit cavity coupling. So by acting this identity operator, we are essentially decoupling it from the cavity. And so here is control pulse that Rusch has found. And so here's the envelope of the wave, and there are actually 3 waves in the x, y, and z directions. And the gate is actually 10 nanoseconds. And this is the evolution of the qubit that the gate causes. As you can see, nothing is happening. The final state is the same as the initial state, which is what we want. And I've also found control pulses that actually change the state of the qubit, such as the NOT gate and Hadamard gate I talked about earlier. And so here's the control pulse for a NOT gate. And this is the evolution it causes. And so it starts off in the completely in the 0 state, ends up completely in the 1 state, which is the desired behavior. And here's the pulse for a Hadamard gate, which causes this evolution, where we're starting in the 0 state and ending in a superposition. And while I'm only showing one set of initial conditions, the gate works for any set of initial conditions. And so finding these wave pulses will help us design fault-tolerant quantum gates, or I mean they are quantum gates that are fault-tolerant, we hope. Meaning that they don't introduce any error into our system. And so the next step for this project is to find control pulses that for 2 qubit gates. One more. So I'd like to thank my mentor, Felix Montsalek, who's right here, and Professor Whaley for letting me work with the group. And I would like to thank the Louis Scholarship Foundation as well.
Questions from Miles? Questions?
Why did it go to 0.7 instead of 0.5?
Because, sorry, the question is why is the final state 0.7 and not 0.5? It's because this is the probability density, so we need to square the probability density to get the probability, which needs to add to 1. And so 0.7 is about 1 over the square root of 2, and so we square that again.
For your gradient descent, how do you sample the state of the system without it being disrupted?
Sorry, what was it?
How do you sample the state of the system to proceed
Oh,
without it being disrupted?
so, well, the gate is a unitary operation, which it's not an observation. So you essentially evolve the system without doing a measurement, which would destroy the system. But then you measure it at the end to see what the unitary operation did. I'm actually not working with a physical system. I'm simulating this on a computer.
So in other words, you calculate ahead of time what the impulse function should be, or what the function should be through to the algorithm?
Yeah, we come up with the controls, the control pulses that will affect the Hamiltonian of the system. And with the Hamiltonian, we can find the unitary operation of the evolution.
So you just do that exhaustively, or you have to do
He's
that?
figuring out how to do this with your qubit without having it not do it.
Okay.
He's figuring out how to do this with your qubit in the hand work, without doing anything else.
Yes, sir, yeah.
So he measures it here and here.
But you do it, mathematically, or you do simulation?
Yeah.
Which?
Simulation. In a physical system, we just start an initial state, act the unitary operator, and measure the gain.
Any other questions from Mark? In the back, maybe?
Yes, no?